In Chapter 19, we will be looking at aromatic substitution reactions. So you've already seen what makes up an aromatic compound, and now we can see what kind of reactions we can do with and where we can find them. So the two structures that you see here are part of the components of food coloring. This one down here is the structure of red number 40 with aromatic groups here, and then we have over here yellow number 6. And both of those, other than the aromatic rings, have these double nitrogens in common, which is an azo compound that is in a lot of dyes. So in Chapter 9, we learned about different alkene reactions, and we saw that if you have an alkene and we add bromine, that will do a transbromination across the double bond. If we try to do that same reaction with benzene, we're not going to see a reaction. This does not occur. If you want to do that reaction, we need to add iron as a catalyst in order to brominate benzene, and only one bromine gets added. These reactions are called electrophilic aromatic substitution reactions, or EAS. With these reactions, with this type of reaction, we can do several things, including put bromines on chlorines, we can add a nitro group to the benzene, a sulfonate group, an alkyl group, or an acyl group. So we'll look at all these reactions in this chapter. To promote an electrophilic aromatic substitution reaction between benzene and bromine, we need to have iron present. And when iron is there, we have 2Fe plus 2Br2. That's going to create 2 molecules of iron tribromide. And when that is present, one of the bromines will attack the iron, get a new bond forming here. This bromine is making 2 bonds, which it doesn't want to do, so it will be positively charged, and this iron has extra electrons, which it also does not want, so we get this minus charge. To alleviate that, this bromine can go there and give up its electrons to this complex. We end up with FeBr4 plus Br plus. If you recall here, these electrons were given up to give it to the bromine, and now this bromine is short a pair of electrons. Once that complex forms, the Br plus and the Br minus, this makes a very good electrophile because we have this positively charged bromine, and we have a nucleophile. So this nucleophile can grab that electrophile or attack or hug that electrophile. Those electrons go on to the bromine to form that FeBr4. So when I take those electrons out, the Br gets added here, and then I have a positive charge. Then I have that positive charge there. This is called a sigma complex. And this particular compound is resonance stabilized, and we'll draw those resonance structures here. So the positive charge can move there. It's still stabilized by resonance. And the positive charge can move out there. So this reaction can happen because the ring is resonance stabilized. So from here, what we can do, we have the BrFeBr3. This still has a minus charge because it has that extra bond to bromine. That's going to act as our base, and we'll grab this proton, and these electrons will go in to form that double bond. The iron is still negatively charged because it's making the extra bond to bromine that it doesn't want. So what we can do is take these electrons from this bond and use it to grab the hydrogen. Those electrons will go in to form the double bond. So we get that double bond, we get benzene. We also formed HBr in the process from this Br here. And then FeBr3 is regenerated. You can also do this reaction with AlBr3. If you want to add a chlorine to the benzene ring, we can do that as well using similar conditions. You get HCl plus 85% of the chlorobenzene. The mechanism is similar. This H is going to grab this, The sigma complex forms. You can practice drawing the resonance structure here, but I'm just going to move on. So there's the sigma complex. We have ClAlCl3. These electrons are going to grab the hydrogen. We reform benzene. So we can do this reaction with bromine and chlorine. F2 is too violent. And I2 is too slow. We will see methods later on to add fluorine and iodine to the ring. There's many different electrophiles that can be attacked by an aromatic ring to give you several different products. If we have benzene with fuming sulfuric acid, we will add a sulfonate group, or SO3H. And the way that that works, the S is acting as our electrophile. Benzene is our nucleophile. Get a nucleophilic hug on the sulfur. So one of these electrons will go up in that process. So we have SO3 minus. That same sigma complex is formed. We can draw another resonance structure. And those are our sigma complexes. With water present, that's going to act as our base and do a proton transfer. Then once we reform the benzene, this O can get protonated. And that is the mechanism for that reaction. If you have concentrated fuming sulfuric acid, that will put the SO3H in place. But if we do the reaction with dilute H2SO4, that will remove that group. Another reaction that we can do is adding HNO3 with sulfuric acid. When you have nitric acid in the presence of sulfuric acid, the OH group can grab a hydrogen. Those electrons go on to the oxygen there, and then we're going to do an elimination of the water group that forms to form this nitronium ion, which is a very good electrophile. And benzene again is going to act as our nucleophile. So we have the nucleophilic hug. Nitrogen is still positive, and that's positive there. We can draw our sigma complex resonance structures. And then one more resonance structure. And the water present can grab this hydrogen and do the elimination. And then we've added the nitro group. Once you have the nitro group, we can actually reduce this to form an amine. Iron or zinc with HCl will give us NH2. If we do a two-step reaction with nitric acid and H2SO4, followed by zinc HCl, we form aniline. Another reaction we can do is a Friedelcraft's alkylation. We add chlorine, an alkyl halide, or an alkyl chloride in this case, in the presence of aluminum trichloride. We get benzene and the addition of the group that was attached to the chlorine. So this is where it would attack. When you do this reaction, a carbocation is generated when the chlorine attacks the aluminum trichloride. So the lone pair of the chlorine is attracted to aluminum. So we have a bond here. Chlorine is positive because it's making more bonds than it wants to. Aluminum is negative. And this now is a really good leaving group. So this will leave and get a loss of a leaving group. Carbocation forms there. We get this plus Cl, Al, Cl. We get aluminum chloride. So once we have that carbocation, the benzene is free to attack that one. So nucleophile and electrophile. This is usually a water workup. And that's how we get the product. This would happen in 66% yield. If you try to add chlorobutane with aluminum trichloride, we're going to get two products. We'll get the product that you probably were expecting, plus this one. And probably more of the one that you didn't want. The reason that this forms is once chlorobutane reacts with aluminum trichloride, we can get a hydride shift when that carbocation forms. The secondary carbocation is formed. So this one is due to the rearrangement. There are some limitations that we'll see with the Friedelcraft alkylations. The first is that the halide leaving group must be attached to an sp3 hybridized carbon. If you have a chlorine on a double bond or the chlorine on a benzene ring, this will not react. So there's no reaction with either of these reagents. In the last slide we saw it with chlorobutane, and before it was a 2-chlorobutane. In both of those cases, the halogen was on an sp3 carbon. If it's on sp2, it will not work. When you do this reaction, it can occur more than one time, so we can get polyalkylation, where an alkyl group will add more than one time. The third thing is that if you have strong activating or deactivating groups, you will get no reaction. So an NO2 group, this is strongly deactivating. So we get no reaction. And we'll talk later in the chapter about what groups are strong activators and what groups are not strong activators. We can do a Friedelcraft acylation. In an acylation reaction, we form a new carbon-carbon bond. In both the acylation and alkylation reactions, we form new carbon-carbon bonds. In an alkylation, we're adding an R or alkyl group. In an acylation, we're adding a carbonyl R group. So this is referred to as an acyl when you have that carbonyl with the R group here. So benzene with the acyl group, just like in the previous example, everything on the other side of the chlorine was added. We're going to do the same here. We have this good leaving group. This is called an acylium ion, which is resonance stabilized. and we shift the positive charge to the oxygen. So the acylium ion usually does not rearrange because of resonance. Some alkyl groups can't be attached by a Friedelcraft reaction because you have the worry of rearrangement. So many primary alkyl groups you're going to have a hard time adding. What you can do instead is an acylation followed by a Clemmensen reduction. If I wanted to add this acyl group, so everything on the other side of the chlorine gets added. This is followed by zinc amalgam with HCl and heat. So similar reactions to reducing that nitro group to the amine. And we get the alkane that was added. We usually don't get polyacylation with this reaction. And now we've added the alkane chain without having to worry about rearrangement.